So in this video, we're going to talk about the idea of formal charge and how do you get, right, how do you come about getting the formal charge for each atom in a molecular formula, as well as, maybe some resonance structures, and how would you choose the formula or the molecular compound with the lowest energy or the best formal charge possible. So let's look at this compound. So right, so let's look at this compound, right? What if I asked you what is the formal charge of the nitrogen atom? How would you do it? Well, there's a whole bunch of complicated formulas out there for formal charge, right? But I'm going to make it simple for you. So the formal charge formula that I use is simply the number of valence electrons, right? So number of valence electrons the atom has. So number of valence electrons of the individual atom you're looking at, minus the total number of electrons around it. Around it, right? So the number of valence electron of the individual atom minus the total number of electrons around it. Now this minus total number of electrons around it, it sounds really weird, but I want you to see very carefully what do I mean. So let's say they ask you on an exam, okay, what is the formal charge of nitrogen? How would you do it? Well, I'm going to look at a periodic table and say, okay, well, nitrogen has a valence electron, number of valence electron, it has 5 valence electrons. So that's part 1 in the formula. I'm going to subtract that from the total number of electrons around it. So this total does not mean I count these double bonds as doubles. So what do I mean? The total number of electrons. So if you look at nitrogen, this bond is 1 electron from chlorine and 1 electron from nitrogen. So I'm only looking at that 1 electron from nitrogen, and it's the same thing on this side. So I'm looking at the individual total number of electrons around it. Again, this electron is from nitrogen, while this pair of electron is from chlorine. I do not care about the chlorine. I only care about the nitrogen, right? So let's count how many, and it's the same thing for here, right? I do not care about chlorine's. I do not care about chlorine's valence electron, but I only care about nitrogen. And so this needs to get off my screen, right? And so when we count the total number of electrons around nitrogen, this is 1, 2, 3, 4, 5, right? So this is 5 minus 5, which is equal to 0. So nitrogen in this case does not have a formal charge. Let's look at chlorine, right? I'm going to take chlorine's valence electron, right? Which is chlorine has a valence electron of 7, right? And then I'm going to count the number of individual electrons around chlorine. So I have 1, 2, 3, 4, 5, 6. Remember, this is a single bond, but remember, this one is coming from nitrogen. I do not care about this one. I only care about the one that's coming from chlorine. So this is 1, 2, 3, 4, 5, 6, 7. Right, so that means I have 7 valence. So I have 7 total electrons around chlorine, which will be 0 as well. It's a nifty trick, but it works. Let's see if we could go to more complicated problems. Again, if I did this to one chlorine atom, the other 2 chlorine atoms are in the same place, and so this problem is kind of boring, right? But we must start off easy. Let's go to a more complicated one. Let's say we're given a series of structures. So let's say we're given CO2. We're also given this formula as well. And we're also given this formula as well. So right, so we're given 3 formulas of CO2. Essentially, what we call resonance structures, right? How do we calculate the individual formal charge in these atoms? Well, we're just going to go back to a nifty trick that we spoke about earlier. We're going to take the atom valence electron. So let's look at this oxygen in this case, right? So oxygen on the periodic table has 6 valence electrons. How many total electrons do we have around oxygen? Remember, we have 1 and then we have 2, right? From the double bond, right? So again, 1 is from this carbon, this, right? So these 2, let's split this double bond so it can make sense. So these 2 are pertaining to this carbon, right? So we have 1, 2, 3, 4, 5, 6. So this is essentially 6 minus 6. So the formal charge on this oxygen should be 0. Let me show you. All right, let's look at carbon. Carbon has a formal charge of 4. I'm sorry, not a formal charge, but if you go on the periodic table, carbon has a valence electrons of 4 electrons. Let's count how many total electrons do we have around carbon and then subtract it. Remember, we have 1, 2 from this carbon, and then we have 1, 2. Remember, the other 2 electrons are pertaining to oxygen we do not care about. So this is 1, 2, 3, 4. So this is 4 minus 4, and this should also be 0 as well. Let's do oxygen and see if you can continue to do it and see if you can get it. Pause the video and guess and do it and tell me what the formal charge in this oxygen would be, right? So this is 1, 2, 3, 4, 5, 6, right? Remember, so we take the look at the periodic table. Oxygen has 6 valence electrons, so we take 6 minus 1, 2, 3, 4, 5, 6, right? So this formal charge would also be 0. Well, remember, we're only looking at the individual. I can't stress this enough, but individual, so I'm not counting my bonds, but individual electrons around the oxygen. Let's look at this one. What will be the formal charge of this? Well, again, in this case, I'm going to look at the periodic table. I have oxygen, which is 6, right? So I have oxygen has 6 valence electrons. I'm going to minus that from the total number of electrons around oxygen. So this is 1, 2, 3, 4, 5. Remember, it's like an invisible line is there, right? So we have 1, 2, 3. That's only pertaining to the oxygen. So this is 1, 2, 3, 4, 5. So 6 minus 5, and that will give me plus 1. Right, so the formal charge in this oxygen is plus 1. How about this carbon, right? Carbon has a valence electron. I have 4 valence electrons. I'm going to count how many total electrons around carbon. So I have 1, which is right here from this carbon, 2, 3, 4. So the formal charge in this carbon would be 0. How about this? Pause the video and think about what do you think would be this one, right? Oxygen has a formal charge of 6. I'm going to take that in mind. That's the total number of electrons around oxygen. So 1, 2, 3, 4, 5, 6. And I have 7, which is coming from the single bond. So this is 6, the number of valence electrons minus 7, and that will be a minus 1. How about this one? Let's try this one. Let's see if you can get it, right? What is the formal charge of this oxygen in this compound, right? Well, now I have oxygen that has 6 valence electrons again, right? And how many total electrons I have around oxygen? It's 1, 2, 3, 4, and I have 5, 6. So 6 minus 6, so this formal charge is 0. How about the middle oxygen? What is the formal charge? Right? If I look at, oh my goodness, cross that out. But if I look at the middle oxygen, what is its formal charge? Well, oxygen has 6 valence electrons. I'm going to count the total electrons around oxygen. So this is 1, 2, 3, 4. Right? So 6 minus 4, so that will give me a plus 2 on the middle oxygen. How about the last one over here? Right? Carbon has has 4 valence electrons, but how many total electrons around carbon? Well, I have 1, 2, 3, 4, and then 5, and then 6. Right? So essentially it's 4 minus 6, which would give me a negative 2. So now on the exam, suppose the professor asks, well, okay, which one of these compounds would be the most stable? I want you to keep this in your head. The compound that would be the most stable, and it's obviously this compound, right? But why? Put this in your book, write this down. The compound that's usually more stable is the ones that have the formal charges that are closest to 0. right? So the formal charge in any one of your resonance structures closest to 0, that is the best structure. Again, notice I said the total number of electrons earlier in the video because it's important. Students might often get confused and say, okay, well, this oxygen I have 2, 4, 6, 8 electrons around it, instead of seeing that we're only talking about the individual electrons around the oxygen and not the bonds, right? So that's a very important point to make.